possible solutions to that question. And some of them I think are kind of frivolous. I don't really buy into a lot of some of these things. Like the first one, that the math is wrong, the interpretation is wrong, things like that. But when he goes through a number of these, different many worlds interpretations, particles in fluctuating fields, that this is actually not a particle, but an ensemble of particles, and this is the atom, blah, 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 blah. But when there's one, after he goes through his first kind of solution, that the summary that he writes, he says that so many interpretations of the quantum theory have been suggested testifies to the difficulty of relating the theory to reality. For a theory that reproduces the results of experiments so well, this difficulty is remarkable. So, for many years, the most physicists accepted the Copenhagen interpretation, which is what we've adopted. That's the one that says psi is a probabilistic, that's probability in space. That's Copenhagen interpretation. As the best solution to the problem. In recent times, this approach has been called into question, and a vigorous debate is now taking place as to which interpretation is correct. So the point being, it's not settled. They're still debating that. And one of the arguments in here was the one that was relating that you alter the system by thinking about it or by looking at it. So he says that no, this does not exist until you look at it. So the question becomes moot at that point. One of my favorites in this, and it's also in here kind of later, we will see this when we finally get all our molecules in place and finally go down to the atomic level. We're looking at atoms and electrons. Now we're looking at motions. But after this, we'll go to statistics, and then we'll go to electrons and atoms. What we're going to have to do is discover the fourth quantum number. You have three quantum numbers for a hydrogen atom. We have N, L, and M. So you're going to see part of where they come from today. But the fourth quantum number that you call spin quantum number never popped up, didn't exist until P.M. Dirac put in Einstein's relativistic phenomenon. So if he treated now, we resolved all of quantum mechanics, but putting in the general theory of relativity, then spin popped up. It's not spin, we don't know what it is, but it's going to be interesting to see where that comes from. But if you do treat this, and you go back and solve the quantum mechanics again, allowing for the Einstein's theory of relativity, you get an answer that looks like this. In other words, you get a probability that's non-zero in the center of the box. So if you look at a kind of a relativistic quantum mechanics, then the problem never goes away. But I still tell you, it's an illegal question because it's asking a classical question to a quantum system. So how does a particle get from one side to the other is a classical thought. It's not a quantum thought. So the question itself is kind of bogus.
Like, isn't that, you said there was a point of the correspondence theory where the quantum needs the classical, and this is not the case because it's just a random.
Yeah, this is now, so this would be something at the very low level. If we got the energies up sufficiently high enough, then yes, and that's exactly what we see. For the three-dimensional particle in the box, the energy, the quantum levels are so high that it exactly matches what we would expect to see for a ball bouncing around in space. So that's not going to be the case for the systems that we're going to be looking at, but for translation, it certainly will be. Morning. Now then, since we have, again, two particles, three-dimensional space, that's 6 dimensions, we're going to get 6 quantum numbers. 3 of them we now have. We now have half of our system solved. So there's our 3, when we get down again back to the 3D particle in the box, we have our energy, we have an NX, NY, NZ. We now know that system. Now we want to look at internal motion. To do that, we're suffering the same problem that we had when we were looking at the relative, when we were doing Boltzmann distributions and dynamic theory, we had a classical system where we wanted to have a collision rate. We wanted to kind of develop and produce a rate constant. So we needed to know how many particles collided, what's the frequency of collisions. What we had to do at that time is to go into what we call the center of mass coordinate system. This is a re-derivation. I won't do it again because we have already talked about this. But if I have a center of mass coordinate system where I have velocity A minus velocity B, and this is then the velocity of the center of mass. This is the relative velocity and the velocity of the center of mass. If we invert these things and put it into the kinetic energy expression, just like we saw last semester, or I'll even say last year, what we find is that the kinetic energy term will be separated perfectly into center of mass motion and relative motion. This is done. That's the 3D particle in the box. We know everything there is to know about that. Now we want to look at relative motion, and of course now we have this m being the total weight of the particles. It's a benzene molecule, it's the entire mass of the molecule. So that benzene molecule is running around the room, hitting walls, we're done. We know that's going to happen. Now we want to know what's happening to that benzene molecule in relative motion. How is it rotating? How is it vibrating? So that we will now drop down into that system. Now, we're not going to discuss this, but if I do have a multiple system, multiple particles, that center of mass coordinate system that's introduced for 2 particles can be extended to in any number of particles that we want. So if I have a 8-body system, I can do a very similar center of mass type of relationship to that. But anyway, it's just kind of about the point that Raph makes up that is interesting. In this, so now we have our kinetic energy term, and reminding you of classical foundations. And again, classical mechanics is easy. It's easy. Quantum mechanics is hard. So in classical mechanics, I want to just draw a correlation where if you had, a kinetic energy is 1/2 mv squared for linear motion. For rotational motion, the kinetic energy is almost identical, but it has now I, which is the moment of inertia. And that kind of will change depending on what the system is, but we'll be looking at that. And then instead of having velocity squared, this is the angular velocity squared. And of course, the I is the kind of corollary to the mass. That's the distance from the center of the axis. So you know that if you try to push a door from the outside handle, it's easier than trying to push a door open from the inside. That all plays a role within there. And so we have then the kinetic energy as being linear, momentum squared over 2m, p squared over 2m. Rotationally, its angular momentum is L squared over 2I instead of the m. So just showing that there is a pattern that comes within here. Now, the angular momentum in x, y, and z are a result of vector cross products. So if I wanted to know the angular momentum, it's r cross momentum from your dynamics, so you might remember that. Lx squared, Ly squared, Lz squared is L squared, just like r, and x squared, y squared, z squared. But the cross terms, the Lx, that's y times the momentum z minus z momentum y. Ly is z, that's because you're doing a cross product of vectors. And so when you do that, that produces that. And again, I just want to show this for just kind of demonstration purposes. We're not going to extend it. I decided not to. But here is just how, one you could treat just classical rotational motion. So I'll put this up for you, you can play with it to your heart's content. But I have here a mass of atom 1 and 35, so this is going to be HCl, where I have the 35 isotope. HCl is a vibrational frequency, 2989.7 times 10 to the minus 8, and has an equilibrium bond distance of 1.2746 angstroms. This is a worksheet, by the way, that has into an atomic unit system. We'll talk about that when we get to atoms. But when we're getting down on that atomic scale, it's convenient to have a unit system that plays this role. So since MathCAD doesn't know how to do that, I can tell MathCAD what an AMU is or what an angstrom is. But whenever MathCAD does its work, it always converts back into SI units first, which can cause some difficulties when you're dealing on this particular level. So anyway, there's no units, we just understand that's an AMU, that's an AMU. This is a wave frequency rather, and then bond distance is going to be in angstroms, and these are kind of defined here. So AMU, angstrom, and EV is what our energy is in there. But I just have simply a set of coordinates. So I have, atom 1 and atom 2, these are the spatial coordinates. So I'm just going to use the center of mass unit system just to find out what's going on with this particular particle. So first off, here's my relative coordinate system, q of atom 1 minus q of atom 2, so it's the distance between them. And the center of mass is then located here. The mass of atom 1 times its, the coordinate atom 1. And so we know then that the Rx, Ry, and Rz are these particular values. The center of mass is located at X, Y, and Z within there. So from there, I can find the bond length, R squared. Hey, I was warning you. And so you can see that if we just do the R1, we get X squared plus Y squared plus Z squared square root, we get the bond distance. I do the same thing with the center of mass, so I deduce that the center of mass of the particle is about 2.5 then angstroms away from some origin. And then I can just apply all these are just thetas and phi for angular, so I can see that it is oriented 30 degrees and 60 degrees. The center of mass is out 45 degrees and 60 degrees over. And then I can calculate rotational information where I have this R cross momentum, so I can produce those values. So the L sum, so this is the Lx, Ly, Lz, and then we have the total vector. So that's what my only point is kind of just showing this is that classical mechanics is trivial. It's really, really easy to do. And we can always find everything we want to know at any time, at any point that we like. All right, but we're now in the quantum world, so things are going to get a little more dicey now. So from that, what we have to do is now take our wonderful three-dimensional Hamiltonian. Remember, the Hamiltonian is minus h bar squared over twice the mass. In 3 dimensions, it's the second derivative with respect to x squared, second with respect to y squared, and second with respect to z squared. So that is a Cartesian Hamiltonian, which we used to solve the three-dimensional particle in the box. However, for internal motions, for rotations and vibrations, we need to transform from this x, y, and z into an r, theta, phi, to a spherical coordinate system. The math is a little bit dicey to do that. We will not go through it. It's beyond what I want to present, but I will just simply produce for you only the final result. So the Hamiltonian x, y, and z, when transformed into a spherical coordinate system, now becomes something a little bit uglier, right? You have an R term, you have a theta term, and then here's a theta and a phi term within there. So there is the kinetic energy term for the Hamiltonian, and of course we add to that whatever potential that exists. For a rotational system, this phi will be 0, because there's really no boundary there's nothing holding up a molecule from rotating. When we look at vibrational systems, this will probably use Hooke's law to begin with, and ultimately then a Morse potential within there. All right, so again, we're not going to derive that, we're just simply going to use it. And the angular momentum L squared is then this, the only thing that's not here is the 2 mu r squared. Mu r squared is the moment of inertia, I put it in there. So here is our three-dimensional angular momentum term. The x, y's, and z's, when we do that work, it comes out to be here. So if I want to know what is the angular momentum in the x direction, there's a set of operators that do that when transformed, the Ly and Lz. But here's the rub on this. The Lx, Ly, Lz operators mutually do not commute. That means I cannot measure simultaneously any 2 of these values. What I can do is the L squared operator and any one of these do commute. So I'm allowed one bit of information, actually two. I'm allowed to know the total angular momentum, how fast is the thing moving or spinning, and I can only know one of the orientations, X, Y, or Z. So if I were to look at those three equations, knowing that I can only have one, which one do you think I want to pick? Probably that one. That's far easier to work with. So if I'm only allowed one, I'm going to take the easy one from there. On that, just because you probably should do this just once in your life, my homework problem has you derive this. So let me just kind of go through that and get you started on it. What I've got is the LZ is, the operator is minus I H bar, and then this is the X derivative with respect to Y minus Y derivative with respect to X. So just, that is that cross term vectors that you did, okay? So if I want to know what the angular momentum is in the Z direction, I have to do this. Well, this has to be then transformed into then a spherical polar system. So I guide you through in doing that. So I give you first some relationships. One, I said, I give you first that X is R sine theta cosine phi, and I give you a few of these other ones. One that is of particular note is R squared is X squared plus Y squared plus Z squared. And then if, like here is X is R sine theta cosine phi, I have another one that Y is R sine theta sine phi, you have those transformations. When you invert those, you have the following. That the theta is the arc cosine of X, or I'm sorry, Z over R, and phi is the arc tangent. It should be a y over X. Okay? All right, so here's what we have to do. I need these here, dx and dy. Let me do the dy. The dy, when transformed, will be equal to d, let's see, make sure I have it put it in the right direction. Yeah, I give it an x, that's right. No. So it's going to be dr, dy, dr, plus d theta, dy, d theta, and d phi, dy, d phi. And we're going to have another one for the ddx. So I need to find that, and that. And then three others. I'll do the first three. This one is simple. The dr, dy, if this is your r here, then from that, 2r dr is equal to 2y dy, using implicit differentiation. If you choose, you can just take the square root of this and then take a dr, dy, you'll end up with the same result. But we find out that dr, dy is equal to, now we can choose go away, it becomes y over r. So there's one. Now let's do a d theta dy. Well, the other bits of information I've given you were derivatives. I have that the derivative with respect, let me do this, with respect to y, I'll do it this way, is the arc cosine of u times du dy. So this is just right out of a table of math tables, okay? And the other one I gave you is dx, whoops. I'm sorry. I miswrote this, I'm sorry. It's correct on the homework sheet. I apologize, I just wrote it incorrectly here. So you would dy of arc cosine of u. This is written in the homework is minus 1 over 1 minus u squared square root du dx. There. Finally got that one right. And again, that's just right from a math handbook. The dy of the arc tangent of some quantity u, that was also given. This is 1 over 1 plus u squared, and again du dy. Okay, so I'll do these two, and then I'll leave the last three for you to do. So the d theta dy then, where theta is arc cosine of z over r, if I want to, remember that, dr dy was y over r. We had that. So if I want this theta, I need this one right here. So d theta dy is dy of theta, which is the arc cosine of z over r. This, according to my derivative, the arc cosine, this is minus 1 over 1 minus this argument z over r squared square root multiplied by d z over r dy. Okay, so this one here, this will then be minus 1 and 1 minus z over r squared, square root that term, and this is going to be minus z over r squared dr dy. Well, dr dy was y over r, so that goes down in here, and it's all done. So then we'll have a z y over r cubed, then you have this. Now this term right here, the z over r, is the cosine of theta. So what you're going to then end up with is a final result here. You're going to have a 1 over 1 minus cosine squared of theta square root times a z y over r cubed. And that's the one I did in the in the notes. I'll do one more. Just do the d phi dy.
What if we get from dz over r to over dy? What we have
For here?
right above it. So
Here?
yeah, that term.
What about it?
Down to the next one. How do we get z?
Well, this, we're taking z, of course, is not a function of y. So, but r is, so it becomes minus z over r squared times dr dy.
Oh, I got it.
See it? Yeah, because you're taking, what is the derivative of z over r with respect to y? Well, r has y in it, z doesn't, so it's minus z over r squared, then dr dy, just using kind of a chain rule type of thing. Let me do the d phi dy. So there's 1, dr dy, there's 2. So d phi dy is the derivative dy. Well, phi is the arctangent of y over x. So I just kind of put that in place. Well, then I use my integral tables or derivative tables that I just got from the math handbook. So a derivative of arctangent of some quantity, this becomes 1 over 1 plus this argument y over x squared, just follow the bouncing letters there, times the derivative of that argument y over x dy. I'm just following exactly what the math tells me to do. Well, this one then, now y over x is, that where's it, right here, y over x is the tangent of phi. So it becomes 1 over 1 plus tangent phi squared. And the derivative of y over x with respect to y just becomes 1 over x. So that's the answer. So that's d phi dy. So this one then, you put that into that chain, then you'll have to do a second one for d dx, which is almost identical. And then when you finally put it together in that LZ operator, then you will find that it will drop down into this term. Everything will go away. It'll end up being here. So, like I said, you should see this do that once, once only. I won't actually do it again.
One more problem number was that?
That's problem number 1 in the rotation. Okay, so I did half this, so you get half. All right. With that now, here is now our rigid rotor system. What we'll do is, for the moment, is we will fix the bond length in place. We won't allow the molecule to migrate. Now, this is going to be a concern later. Just think about this. Just think about it classically if something is vibrating and rotating. Just think about that whole ice skater problem. As the molecule then contracts in its vibration, it's going to spin more quickly, and as it stretches, it's going to slow down. So you're going to have this coupling back and forth. We're going to have to ask the question, how severe is that coupling in a molecule? So what will it come out to be? But for the moment, what we will do is we will fix the bond length at some fixed value. When I go to my Hamiltonian up above, so here's my Hamiltonian now. If we fix the bond length in place, that term is 0. So we have only the thetas and the phis to contend with. So if I remove that r term, now we have our Hamiltonian is minus h bar squared over 2I, a moment of inertia, where the moment of inertia for a diatomic particle is mu times the bond length squared, which is our constant. Then we have just all the derivatives with the theta and the phi. That is the Hamiltonian. There is no potential, because we're presuming we have free rotation. So here's the Schrodinger equation, h psi is equal to E psi. Put everything back in place. Then I have to do a little bit of manipulation to get it into a form that I need. With that, I will end up with something that looks like this. Again, it's just a little bit of arithmetic to go in there. It is, like we've seen before already, it is a differential equation that has 2 variables in it. So what I have to do is to do another separation of variables. So I will say the wave function is a product of a theta term and a phi term. So I'll make these products. There is no potential coupling all these things together, so they ought to separate very, very nicely. When I put everything together, doing a separation of variables just like we've done it a couple of times already, I arrive at this. Notice that here is a grouping that is strictly in theta. Then I have just this, which is strictly phi. So in other words, I have just a theta part and a phi part. Both of them are independent of each other, but when added, show to be 0. When we did a separation of variables like this several times now, the only way that could be true is for this and this to be equal to a constant. When I do separate those things out, I call the constant m squared, and that is, by the way, when you talk about m sub l, you know, in the quantum numbers, that's where it comes from. The solution to the hydrogen atom is going to be identical to this. It's just going to be interpreted differently, okay? But the hydrogen atom will produce an m sub l that is identical to this. So we have a theta differential equation here, which is really, really ugly. And then we have a phi differential equation here, which is really, really sweet. That one we can solve immediately. So let's look at that, just the phi term. So of this, I have that 1 over the wave function in phi, then second derivative of phi with respect to the coordinate phi. Notice the capital phi, and I'll do a lowercase. This is minus m squared. Rearranging d2 phi, the coordinate phi, plus m squared phi is equal to 0. So all it is multiply through by phi, bring everything to one side, and there is, of course, our very, very familiar differential equation that we had introduced earlier. This one, it has a positive sign here, so all I need to do is to write down the answer. So if I write down the solution, phi, now as a function of this coordinate, is going to be a e to the I m phi coordinate, b e to the minus I m phi coordinate. So that is then the solution. Now, we have to apply a boundary condition. Well, this boundary condition is a cyclical thing, and it's going to produce exactly the same criteria as when you were doing that particle on ring. What we have is to ensure that the wave function is single valued, I must have that phi as function little phi must be equal to the wave function after I go around a full 360 degrees. So if I go all the way around, then the wave function has to have exactly the same value to be single value. When we did this, and I will just take one term, when you did this, I think you remember, I'll do this term here, then we have to say that a e to the I m phi must be equal to a e to the I m phi plus 2 pi, my boundary conditions. The lower, or this term here, becomes a e to the I m phi times e to the I m 2 pi. If I break up that, exactly what we've done before. This is what we saw in our particle in the ring. This here, quantum number. So the differential equation originally in here, with a few different substitutes, and I've done it over here to the right, we end up with something that looks like this, and this is called the associated Legendre's differential equation. We will not solve it, I will just present you the results. So when you did all this little bit of algebra in here and transform these things back into place, you produce a set of polynomials. The j is your quantum number. Okay? This, again, comes about because when you solve the differential equation, the series has to converge. It cannot blow up. When doing that, this j becomes quantum number 0, 1, 2, 3. What is also included, these quantities, the p of x here, are called the associated Legendre polynomials. They are a series, you can generate them, and we'll talk about the products of those in just a moment. But this is P, the lower and upper are L and M, as we will see. Let me come down here. So the polynomials that result, they have a lowercase, that's one quantum number, then the upper one, which is the other quantum. So here's your two quantum numbers. And so the P00 polynomial is 1. The Pjm0 polynomial is just x, and so forth and so on. Keep in mind that this x here is the, where I have it here, x is cosine theta, okay? So whenever I want to now represent this for my molecule, I'll say, all right, what is the wave function for a J equal 1, M equals 0 quantum state? Well, this X becomes cosine theta. So the answer is cosine theta. But that's how it's represented anytime you look it up in a math handbook or textbooks and things along that line. So these polynomials, there's just there are about 5 of them here that will probably be all we will need, but they can be generated. They have a set of what are called generating functions. So if I wanted to generate the 3-2 polynomial, I would simply follow this rule. It says first I need for P3, I need a P3, so the P3 says take 3 derivatives of 1 minus x squared, and all these put together. So again, we're not going to do that, but I just want to say where these things come from, so it's not a mystery. This one we will use, they have recursion relations. This says if I know the J and the J minus 1 polynomial, I can use this to get the next one. So I can kind of cycle it over. That's how MathCAD does it. MathCAD has built-in programming and it has Legendre polynomials built into it. But if I want to generate a next polynomial, it just does this. So we can always generate one. There's one, the derivative that comes into play, and then these are when put in the J1's recursion relation. So we can I'm just showing you how these things are put together. Ultimately, we will have our wave function. We're not going to need to do a lot of this, but I want you at least to have seen it. They are orthogonal, wonderful, because they're the operators are Hermitian. So any integral over one polynomial to the other is 0 if J is not equal to K, and if it's normalized, it'll be 1 if it is not. Okay? Now, returning to the original rotor problem, the beta in that differential equation is J times J plus 1. That is 2IE over H bar squared. So the energy, so here's now where we're getting things that are useful now. This energy is J times J plus 1 H bar squared over 2I for a rotating molecule. Notice that the energy does not depend on M. It only has a J in there, so we're going to end up having degeneracies, you will see. And we will be able to lift that degeneracy later. So putting it all together then, so there's the energy, we will need that. Here's the angular momentum, we may want that. Now, I put the entire wave function together. I go back, I get my phi term, I get my theta term, and I put it together so we have a normalization constant, N, J, and M. I have the Jm, polynomial, Legendre polynomial, e to the ion phi, which is our solution there, and the normalization constant ends up being 2j plus 1 over 4 pi, j minus your quantum number, m absolute value, subtracted factorial, and plus 1 factor. So we can always then generate then the normalization constant from that. So that's everything we have. We have the wave function. Everything we need to know is contained within there. And so when we come back, we'll start asking some questions. So I want to know how the molecule is oriented. How is it rotating? What sort of limits does it have on its rotation? How fast is the molecule rotating? This will go to answering questions in microwave spectroscopy. Because microwaves are rotating molecules. So I want to know how fast these things rotate. That way I know what radiation to hit it with to get where I need to be. And then finally, what is the distribution of rotational states at some given temperature? This last one, we will deal again with quantum statistics. In order to find internal energies, enthalpies, entropies, I need to know how many particles are rotating in what way. So we'll be able to get that later. We'll get very, very good answers out of that. And then, of course, there's that same question that we'll have to address. In the translational system, we found particles were in such high states, the energy levels were so close together, we could treat it as a continuous integral. And we could almost treat it classically. We'll have to ask the question here, can I do that with rotation? All right, that's going to be a question we'll have to kind of deal with from there. But there, that is, and we'll start answering these questions then next time. So problem number 2 in the homework has you go to this right here, where I have my beta defined as, You have a beta right there is 2IE over h bar squared. So having that in place and having then this differential equation in here, don't worry about the phi term, okay? Just worry only about the theta term, or the theta part of the differential equation. In other words, this right here. So that's when you want to look to right there. You know, right, sitting right there on the very top of page 6. What I have given you is a wave function. So we have a wave function theta, now capital theta of the coordinate theta, as being equal to, I have an n times the sine squared of theta. So that is a wave function. There's a solution to that. And I say, given that this is equal to 6, what would I have here? Actually, no, nothing. I say that the energy is equal to 6h bar squared over 2I. And m is equal to plus or minus 2. With those provisors and this wave function, just simply carry out these instructions right here. You'll set this before here. So then you take your beta, put it in here, and then take the wave function, that sine squared theta, take a derivative, multiply by sine theta, take the derivative again, multiply by sine theta, and show that it is a solution. So it's just following the derivative instructions as it goes. So those two are a little bit lengthy, so if you run into a little struggle, we might kind of put one of those off of that if you want. I didn't mean to put too lengthy, but I got some really short, easy ones coming. How about that? I'll make up for it later. So anyway, we'll start answering some serious questions about how molecules are rotating, what the orientation is, what the type of it, and what the energy difference between those. And then we'll be down finally to vibration. We'll have it all. We'll know everything about molecules. A lot in this chapter. For problem number 2, this is helpful. I just pulled this from the CRC math handbook, so I just want to give you a little bit of help when you get faced with an integral.
If we get a help, it's like, it's gonna be long.
You know,